Good morning, sir.
Good morning.
How are you, sir?
Yeah, I'm fine. And you?
I'm also fine, sir.
Oh, good. I'm trying to share the slide again. I have some problem.
Yes, sir. There are
Yeah, but
still 20 to 25 minutes left to start the lecture.
okay. Yeah. I'll try.
So your presentation is not full in full screen mode.
How about this?
No, sir, still not in the full
Oh,
screen mode.
okay. I'll try again.
Sir, instead of sharing a window, please share your whole screen, entire screen.
Okay. Let's see. How about this?
Now is it fine, sir? It's fine, sir.
Fine?
Yes, sir. It's fine
Oh,
now.
okay. Professor, how about this?
It is fine, sir.
Fine. Okay.
Good morning, everyone. On behalf of Dr. Rohit Mehra sir, Professor at Dr. B.R. Ambedkar National Institute of Technology, and Professor Shinji Tokuname, sir, our esteemed foreign coordinator, I extend a warm welcome to all participants on the third day of the GIAN course. Without further delay, I now invite Professor Shinji Tokuname sir to commence the first lecture of today's session on the dosimetry of radon isotopes.
May I start?
Sir.
Okay.
Sir, please share your entire screen rather than sharing a window.
Okay. Wait a moment. Can you see my slide? On
Yes, sir, it's
screen?
visible, sir. Yes, sir.
Okay. Okay, thank you. Okay. Hello, everyone. I'd like to start today's lecture, but yesterday in my yesterday lecture, it was not enough to explain this table. This is very important, and we can understand the historical history of ICRP publication in terms of those conversion factors. So I'd like to repeat again. So 1987, from the dosimetric approach, ICRP gave us two different dose conversion factors, indoors and outdoors. From publication 50, 6.4 indoors and 8.9 for outdoors. 1993, based on the epidemiological study, they gave us two values, 5 millisievert per working level month at workplaces and 4 millisievert per working level month at homes. This is the publication 65. 1 year after, ICRP developed the human respiratory tract model dosimetric approach, and they gave us the dose conversion factor at workplace 13.4. Although there was 1 year, but the value is quite different, 5 and 13.4. Then, in this value was calculated based on RADEP. This is Radon Dose Evaluation Program, developed by Barchow and James in 1994. After that, in 2000, based on the dosimetric approach, other researchers proposed 15 millisievert per working level month at homes with the same evaluation program. But this program, RADEP, was not available for users, normal users. Therefore, my colleague, we check the conversion factor using the general program, namely RUDEP, Lung Dose Evaluation Program. According to this analysis, we got 13.7 at work, 14.3 at homes. The results were very similar from those calculated by RADEP. In 2010, based on the epidemiological study, they gave us two values. They are 9 at work and 7 at home. In this calculation, the lifetime excess absolute risk LRAR was changed from 2.8 times 10 to minus 4 to 5 times 10 to minus 4. These were calculated using ICRP 60 determinant adjusted nominal risks. 4 years after, using the ICRP publication 103, they recalculated the dose conversion factors for both workplaces and homes. As a result, there were 12 at work, 9 at homes. In the latest analysis, ICRP 137, publication 137, gave us 10 millisievert per working level month. Yesterday, I received Professor Mera about the difference among different dosimetric models, So they were answers. This table shows the dose conversion factors using dosimetric model. Here's the publication, ICRP publication 50 in 1987. Model type is NEA. Here is dose conversion factors I mentioned in the previous slide. Second, Anskia 2000. The same as publication 50. They gave us 5.7 indoors and outdoors, the same value. And Hare et al. In 1996, 9.6 millisievert per working level month indoors and in mines. Polstendorfer 2001, based on the Zoc model, they gave three different working scenarios. 8 at home, 11.5 at workplaces, 10.6 outdoors. At home, there was no aerosol sources. Actually, home without cigarette smoke, non-smoker's house. Next, Winkler, Hale, and Hoffman gave 7.6 millisievert per working level month at home, based on the deterministic airway generation model. Winkler, Hale et al. In 2007, the model type deterministic airway generation model and stochastic airway generation model and human respiratory tract model, ICRP publication 66 model. They compared the difference between three models: 8.3, 8.9, and 11.8. Marshall and Barchow gave us 15 millisievert per working level month at home, based on human respiratory tract model. James et al. In 2004, based on the human respiratory ICRP 66 model, they gave us 20.9 in mines and 21.1 at homes. Marshall et al. Gave us 12.5 and 12.9 in mines at homes respectively, based on the human respiratory tract ICRP 66 model. In this calculation, in mines, no hygroscopic growth was assumed. Here's a review of DCF in published data. ICRP publication 50. The reviews are available. Dosimetric models such as Hoffman et al., Jacobi and Icefield, James et al., and Hare and Pasternak. Anskia 1982, 1988, 1993. The same model was provided by NEA as ICRP publication 50. Anskia 2000 recognized that more recent calculations with new dosimetric models such as human respiratory tract model result in higher values of DCF, dose conversion factor. However, as ICRP publication 65 gave the lower values using dose conversion convention, ANSCIA 2000 and 2009 decided to maintain the same value as a previous report after considering it was within the range of possible dose conversion factor. In Marshall and Burchell and others made a sensitivity analysis to identify those human respiratory tract model parameters that significantly affect the equivalent dose to the lungs per unit exposure to radon progeny under conditions found in houses. ANSCIA 1988 noted that equivalent dose may vary by a factor of 3 according to the target cells considered. Winkelhel et al. In 2007 compared the result of dose conversion factor using the human respiratory tract model, a deterministic airway generation model, and a stochastic airway generation model with the same input parameter values. They gave us the result of 8.3 to 11.8 millisievert per working level mass. Polstendorfer 2001 calculated dose conversion factors using an airway generation model developed by Zook et al. 1996. It was given as 8.0 to 11.5 millisievert per working level mass. Nominal aerosol conditions in homes, workplaces, and outdoors. Regarding 4.2 to 7.1 millisievert per working level mass, places one dominant aerosol source producing a high particle concentration such as cigarette smoking or combustion aerosols by diesel engines. As you can imagine, if there are more aerosol particles, dose conversion factor would decrease. See? Compare these values. Here is normal aerosol condition. This is high aerosol conditions. James et al. In 2004 calculated dose conversion factors for mines and homes. They assumed the activity size distributions given in Bayer 6 report, 1999. As a result, they got dose conversion factors of 18 to 21 millisievert per working level months for mines and 16 to 21 millisievert per working level months at homes. They considered aerosol growth and presence or absence of cigarette smoke in homes. Marsh et al. In 2005 calculated dose conversion factor using the human respiratory tract model and activity size distributions for mines and homes based on measurements carried out in Europe. As a result, it was 13 received per working level month in mines and homes, which were the same values, same value. ICRP 2010 concluded dose conversion factor should be calculated using ICRP biokinetic and dosimetric models, including the human respiratory tract model and the ICRP systemic models. ICRP provided dose conversion factors for different reference conditions of dosimetric and occupational exposure, reference conditions of domestic and occupational exposure with specified equilibrium factors and aerosol characteristics. There is a main source of variability and uncertainty in calculation of dose conversion factor. I can say activity size distribution of radon progeny aerosol. Breathing rate, model used to predict aerosol deposition in the respiratory tract. Absorption of radon progeny from lung to blood. Identification of target cells and their location within bronchial and bronchiolar epithelium. Relative sensitivity of different cell types to radiation. Regional differences in the radiation sensitivity of lung. I'm explain this parameter in detail. Activity site distribution as aerosol characteristics. There are two definitions. The first one, activity median thermodynamic diameter, AMTD. It is defined as the diameter of a spherical particle that the same diffusion coefficient in air. Diffusion is the random motion of an aerosol particle caused by collisions with gas. Diffusion is the dominant mechanism of deposition in the airways for small particles of less than 0.5 micron. So this is micron, not. It can be measured by diffusion batteries using wire screen sampling. The second, activity median aerodynamic diameter. It is defined as the diameter of a unit density of the sphere that has the terminal settling velocity in air. Gravitational sedimentation is important for large particles more than 5 microns. Internal impaction is a dominant mechanism in the airways for large particles of more than 2 microns. This is also, here is micron. It can be measured by low pressure cascade impactor. There is a relationship between two diameters. AMTD equals AMTD square root 1000. Here is a shaping factor over particle density. This slide shows the classification of radon progeny aerosols with their particle size, parameter, aerosol size, expression of diameter, particle density, and shaping factor. Here's unattached. It's attached. Attached fraction includes nucleation mode, accumulation mode, and cause mode. Aerosol size 0.5 to 10 in attached mode, 10 to 100 in nucleation mode, 100 to 1000 in accumulation mode, more than 1 micron in cause mode. You see, this is air activity median thermodynamic diameter, and this is a activity median aerodynamic diameter. So there is particle density in kilogram per cubic meter, 1000, 1400, 1400, and 1400. Shaping factor, this is 1, 1.1, 1.1, and 1.1. These are samples of particle size, activity particle size distribution of radon progeny aerosols in the environment, actual environment. Probably I show you in my last lecture, we measured particle size, activity particle size distribution in an underground mine in Japan. Here's an attached mode. Attached mode. There were 2 peaks. On the other hand, we conducted particle size distribution measurement in an actual dwelling. There was no unattached peak, but we found 3 modal peaks in nucleation mode, accumulation mode, and cause mode. This slide explains the behavior of radon progeny aerosols in the respiratory tract. The smallest size activity deposits efficiently by diffusion and is largely removed in the nose and mouth. The unattached fraction, about 1 nanometer particles, has limited penetration to the bronchi. If such particles increase in size due to chemical or physical processes in the air, they reach sizes around 5 nanometers. A 5 nanometer particle can effectively penetrate the nasal or oral passages but still deposit in the bronchial region. The amount of radiation that reaches the lung tissue greatly increases in the 3 to 10 nanometers. As the size continues to increase toward 100 nanometers, the effectiveness of the particle deposition decreases. In the size range above 110 nanometers, most of the deposition occurs in the deep lung, AI region. In this region of the lung, there was a very large area so that the activity per unit surface area of the tissue is very small. For large particles above 2.5 microns, the deposition is mainly in the nose and mouth. Very few of those particles reach the critical target cells of the lung. The size of the particle containing the radioactivity in the environment is very important in determining its effectiveness in delivering dose to the tissue. This figure exemplifies the dose conversion factors expressed in millisievert per working level month as a function of particle size calculated with the human respiratory tract model for a standard worker. Unit density and unit shapes was assumed in this calculation. Here is a relationship between particle size and effective dose in millisievert per working level month. As you can see, the smaller particle give us high dose, radiation dose, but on the other hand, there are more accumulation mode particles in the environment. They gave us small radiation dose. But in the case of coarse mode particles, again, these coarse mode aerosols give higher radiation dose. Therefore, we have to calculate if you have a activity particle size distribution data, you can calculate the dose conversion factors very precisely. The sensitivity of lung dose from inhalation of radon progeny to aerosol parameter values. The variety of dose conversion factors. The dose conversion factors can be written by a function of the unattached fraction. For example, for an adult at home, the dose conversion factor can be expressed in this equation. DCF equals 11.35 plus 43 times unattached fraction. The unit is millisievert per working level month. For an attached fraction ranging from 0.04 to 0.2, the dose conversion factor varies from 13 to 20 millisievert per working level month. Activity site distribution of radon progeny depends on the exposure conditions, namely 10 to 21 millisievert per working level month for homes, 11 to 26 millisievert per working level month for workplaces, 56 millisievert per working level month with air cleaner. Actually, unattached fraction was 0.56. As I mentioned in the previous slide, much smaller particle gave us a significant radiation dose. This is the reason why this value is higher than others. This table summarizes values of effective dose per unit exposure to radon progeny calculated with a human respiratory tract model for different exposure scenarios. Adults at home, home without cigarette smoke, non-smoker's house, around 13, between 13 to 21. On the other hand, in smoker's house, 10 to 16 or 18, the dose conversion factor is smaller in smoker's house than in non-smoker's house. Workplace indoors, 21, 20. This is my paper. So I set the different air conditions. We measured unattached fraction and air cleaner operation. In mines, the dose conversion factor 11 to 26. Yeah. Next, breathing rate. I'll show the different breathing rates for a Caucasian population at different levels of physical activity. These data are coming from ICRP 66. They are classified with age and gender. Resting or sleeping, sitting awake, light exercise, and heavy exercise. See? The difference breathing rate ranged from 0.2 to 3 cubic meter per hour. This parameter is also dominant for dose calculation. Here are the dose conversion factors for different levels in physical activity under typical indoor exposure conditions. After considering by breathing rate also age and breathing rate, age, or any other biological parameters, the lowest dose conversion factor was given here. Adult female, 3.6. The highest dose conversion factor, in that case, 10-year-old male, 80, during the heavy exercise, 80.6. Here is the dose conversion factor for different ages under typical home exposure conditions. This is non-smoker's house and smoker's house. 3 months, 9.6. Smoker's house, 8.2. 1 year old, 11.3. 9.8 in smoker's house. 5 year, 11.3, 9.4. 10 year, 13.5 in non-smoker's house and 10.4 in smoker's house. 15 year, 11.4, 11.5 in smoker's house and 9.0 and 8.8 in smoker's house. adult 12.9, 12.7 in smoker's house, 9.9, 9.9 and 9.2 in smoker's house. As you can see, the dose conversion factor in smoker's house is always smaller or higher than that in smoker's house. In this calculation, there are assumptions age-dependent parameters, mass of the target tissue, respiratory frequency, and tidal volume for each level of physical activity, average time spent at each level of exercise, and lung capacities. Here's a summary of the dosimetry of radon isotopes. There are many types of dosimetric approach. The most important airborne radon progeny from the viewpoint of radiation dose to lung tissue as a consequence of inhalation are the alpha-emitting radionuclides, polonium-218, its half-life of 3.1 minutes, alpha-emitting energy 6.0 MeV, and polonium-214, its half-life is 164 microsecond. Alpha-emitting energy is 7.7 MeV. There are dominant parameters for lung dosimetry are personal or biological and environmental. As you can see, there are various dose conversion factors given with different exposure conditions. Professor Mera, can I?
Thank you very much, sir.
Yeah.
Dear participants, if you have any question, then you may unmute yourself and ask the question. Okay, so if there are no questions, then Tokonami sir, we can take a break of 5 to 10 minutes.
Yep. Okay. All right.
So dear participants, we will start the next lecture at 11 a.m. right after 15 minutes.
Okay.
So dear participants, welcome back after a short break. So we are resuming the next lecture to be given by Professor Tokonami sir.
Okay, wait a moment.
Sir, your screen is not visible.
Okay, wait a moment. Can you see my slide?
Yes, sir. It's okay, sir. Continue.
Okay. Let's resume the next lecture on health effects due to radon isotopes. Here's the history of health effects of radon. 16th century, an unusually high mortality from lung disease occurring in younger workers was observed among the miners in Schneeberg region. 17th and 18th centuries, the frequency of this lung disease, which was later called Schneeberger Lungenkrankheit, Schneeberger lung disease, increased when the mining of silver, cobalt, and copper was intensified. 1879, the disease was identified as lung cancer by Harding and Hesse. 1900, radon gas discovered by Dawn. 1924, radon was recognized as a causative factor for the Schneeberger lung cancer. 1960, first epidemiologic study identified a relation between lung cancer and radon levels. 1988, radon is classified as a carcinogenic agent by the International Agency for Research on Cancer. Radon and lung cancer carcinogenesis. It is estimated that radon causes between 3% to 14% of all lung cancers in a country, then depending on the national average radon level and the smoking prevalence. It is estimated that radon is responsible for more than 21,000 lung cancer deaths each year in the United States. See. Radon and its decay products are inhaled along with air. Radon gas itself is largely exhaled due to its inert nature. However, the radioactive decay products, polonium, bismuth, and lead, adhere to the sensitive lung tissue. Once deposited, these progeny continue to undergo radioactive decay, emitting alpha particles, namely polonium-218 and polonium-214. Alpha radiation has unique characteristics that make it biologically significant despite its limited penetration ability. the high energy transfer capacity of alpha particle enables them to efficiently interact with the oxyribonucleic acid DNA, causing direct strand breaks. Through radiolysis, they generate reactive oxygen species RAS and hydroxyl radicals, leading to oxidative stress. Radon epidemiological evidence in lung cancer. There are different types of study. Cohort studies of underground miners, ecological studies of exposure to residential radon, case control studies of lung cancer and residential radon. Individual studies are usually too small to provide statistically significant conclusions. Here is the limitation of the radon epidemiology. Bayer 6 by National Research Council on Health Risks of Radon and Other Internally Deposited Alpha Emitters. They gave the first comprehensive study on the relationship between radon exposure and lung cancer risk in underground miners, and 4 cohort studies from Colorado uranium miners, Ontario uranium miners, El Dorado uranium miners, and Mount Berget iron miners. The number of subjects are 20,000 miners, more than 20,000 miners. 459 lung cancer deaths. Here's a table on the epidemiological evidence. Here is cohort, number of workers followed, average duration of follow-up, average age at end of follow-up, average duration of exposure, average cumulative exposure in working level months, and number of lung cancer deaths. El Dorado, Beverage, Ontario, Colorado, all exposed, and Colorado less than 2,000 working level months. Based on this data analysis, the excess relative risk per 100 working level months was estimated to be 1.3. 95% confidence interval is 0.8 to 2.3. ICRP publication 65, Protection Against Radon-222 at Home and at Work. They incorporated new studies from regions like New Mexico, Bohemia, and France. There is a projection model, namely multiplicative model, modifying effect of age at exposure and time since exposure. The number of subjects was more than 30,000 miners and 1,047 lung cancer deaths. Exposure risk relationship, monotonic increase of the excess relative lung cancer risk with the cumulative exposure to radon progeny. This table summarizes the result of epidemiological data in different uranium underground mines. Colorado, USA, New Mexico, Ontario, Canada, Beaver Lodge, Saskatchewan, Canada, Bohemia, France. For iron miners, this is Sweden, the total number of miners, 31,486 miners were analyzed. Here is a mean cumulative exposure in working level mass, 120 millisievert. This is a number of lung cancer deaths, observed value and expected value. As a result, the excess relative risk per 100 working level months was estimated to be 1.34. 95% confidential interval, 0.8 to 2.1. This value is very similar to Bayer 6 report. In Bayer 6 report, there are 11 cohort studies. Cohort studies, Europe, North America, Asia, and Australia. 8 of these studies were of uranium miners, and the remainder were of miners of tin and phosphor or iron. The number of subjects was more than 60,000 miners, and 2,600 lung cancer deaths. The lung cancer rate increased approximately linear with increasing cumulating radon exposure. In their conclusion, this table summarizes a different epidemiological study in Bayer 6 report. China, Czechoslovakia, Ontario, Colorado, Ontario, Newfoundland, Sweden, New Mexico, Beaver Lodge, Port Reading Hill, France. As a total, 60,000 as number of workers, and the number of cancers, 2,674. The mean working level months is 164.4 working level months. Mean duration, 5.7 years. The excess relative risk per 100 working level was estimated to be 0.55, 95% confidence interval, 0.27 to 1.13. The excess relative risk over exposure decline with attained age, showing higher risk increases at younger ages. No clear pattern is observed between excess relative risk per exposure and the age at first exposure. Excess relative risk per exposure was found to decrease with either decreasing time since last exposure or decreasing time since exposure. This is a project, relatively new project after 2000. Alpha risk, that is quantification of cancer and non-cancer risks associated with multiple chronic radiation exposures. The 4 countries are involved in this study: France, Czech Republic, Germany. 3 countries are involved. The population size 50,149. Follow-up period 1946 to 1999. Duration of follow-up 26.4 years. The number of deaths as a total 9,933. Cumulative exposure 58 working level months. Duration of exposure 8.8 years. Here's a result on excess relative risk. Czech, French, German, whole cohorts here, EER per 100 working level months, 1.13, 95% confidence interval, 0.974, and 1.53, 0.60 in France, 0.41 in Germany, and low exposure period was selected, and the results are like this: 2.14, 2.11, 3.76. The joint, the 2.60. Therefore, higher risk coefficients are observed at lower exposure levels, and there is strong consistency in the estimates across the 3 cohorts. In Bayer 6 report, Residential Risk Exploration, the conditions of exposure in mines and outdoors differ appreciably. Other determinants of lung cancer risk differ between exposure in mines and indoors. Many of the miners were exposed to other lung cancer carcinogens such as arsenic in addition to radon. A more appropriate way to examine the association between lung cancer and residential radon exposure is a case control study. In the European pooling study, it involved 13 studies from 9 European countries, 7,148 cases of lung cancer, and 14,208 controls. Collaborative analysis of individual data were made from 13 case control studies of residential radon and lung cancer. Measurements were made from residences occupied during the 5 to 34 years prior to diagnosis or acceptance as a control. Here is the title of the paper: Radon in Homes at Risk of Lung Cancer, Collaborative Analysis of Individual Data from 13 European Case Control Studies. According to European pooling study, we can say the mean radon concentration measures in the homes of individuals in the control groups was 97 becquerel per cubic meter, with 11% of homes exceeding 200 becquerel per cubic meter and 4% exceeding 400 becquerel per cubic meter. Among lung cancer cases, the mean radon concentration was 104 becquerel per cubic meter. The dose-response relation seemed to be linear with no threshold and remained significant in analysis limited to individuals from homes with measured radon less than 200 becquerel per cubic meter. It is estimated that radon contributes to approximately 2% of all cancer deaths in Europe. The risk of lung cancer increased by 8.4%, 95 confidence interval, 3% to 15.8% per 100 becquerel per cubic meter increase in measured radon. After correction for random uncertainties in measurement of radon concentrations, the dose-response relation remained linear but nearly doubled in strength to 16%. 95 confidence interval is 5% to 31% per 100 becquerel per cubic meter of estimated mean usual radon concentration. The proportionate excess risk did not vary significantly by study, age, sex, or smoking status. In the absence of other causes of death, the estimated absolute risks of developing lung cancer by age 75 at typical radon concentrations of 0, 100, and 400 becquerel per cubic meter would be approximately 0.4%, 0.5%, and 0.7% respectively for lifelong non-smokers. For cigarette smokers, the risks are about 25 times higher at 10%, 12%, and 60% respectively. There is another study, radon epidemiological study from North America. North American pooling study involved 7 studies from New Jersey, Winnipeg, Missouri 1, Missouri 2, Iowa, Connecticut, and Utah, South Idaho. 3,662 cases of lung cancer and 4,966 controls. In this study, long-term alpha tract detectors were used to assess residential radon concentrations. These data are summarized in this paper. Residential radon and risk of lung cancer, a combined analysis of 7 North American case control studies. According to the North American polling study, we can say average radon concentration ranged from 26 becquerel per cubic meter in the New Jersey study to 127 becquerel per cubic meter in the Iowa study. We found a linear dose-response relationship with no threshold. There was some evidence of decreasing radon-associated lung cancer risk with age. No substantial differences in the access odds ratio by categories of cigarette smoking, number smoked per day, duration of smoking, or time since quitting. For all 7 studies, the risk of lung cancer increased by 11% per 100 becquerel per cubic meter. Cubic meter increased in measured radon concentration, 95% confidence interval, 0 to 28%. When the analyses were restricted to the subset of data with greater exposure accuracy, the lung cancer risk estimates increased. In the Chinese polling study, 2 studies in 2 areas were given in Gansu and Shenyang province. 1,050 cases of lung cancer and 1996 controls. 1-year radon detectors and personal interviews to obtain data on smoking and other risk factors. Actually, they measured radon concentration over over 1 year. For the pooled data, the risk per 100 becquerel per cubic meter measured radon concentration increased by 13%, 95% confidence interval 1 to 36%. There is a linear dose-response relationship with no threshold. These findings were given in this paper. Risk of lung cancer and residential radon in China pooled result of 2 studies. Radon and tobacco gives synergistic effects. Smokers are estimated to be 25 times more at risk from radon than non-smokers. But when I talk in dosimetry of radon isotopes, dose conversion factor in smoker's house is smaller than that in non-smoker's house. The EPA estimates, Environmental Protection Agency in the United States, estimates according to the data obtained by Layer 6 that the risk of radon-induced lung cancer deaths for a lifetime for never smokers is 7 per 1,000, increasing up to 62 per 1,000 for those ever smokers when they are exposed a radon exposure of 37 becquerel per cubic meter. 7 non-smokers, 62 smokers. There is an addictive interaction between radon exposure and tobacco consumption. An increment in lung cancer risk when residential radon exposure increase is comparable to tobacco comparison. Among heavy smokers, the risk was 28.36, 95% confidence interval, 10.91 to 73.73 when exposed to radon levels below 50 becquerel per cubic meter, rising significantly to 73.0, 95%, 19.88, 268.14 at exposure exceeding 147 becquerel per cubic meter. Lung cancer risk increases significantly as radon concentration increases, reaching an odds ratio of 29.3, 95% confidence interval, 15.4 to 55.7 for heavy smokers exposed to more than 200 becquerel per cubic meter. Here. The tobacco consumption. Liver smokers 1 to 33 pack use, more than 66 pack use. Radon and tobacco increased chromosome aberrations in the exposed smokers group are attributed to the synergistic effects of smoking and radon exposure. Chromosome aberrations are reliable biomarkers for DNA damage caused by radon and smoking. Dicentrics in smokers were observed to be 3.8 times higher than in non-smokers. Radon and tobacco, this interaction may be explained by alteration in airway geometry caused by increased mucus production from smoking, along with psychological changes such as silica loss, reduced radon progeny redistribution, and elevated breathing frequency lead to the accumulation of radon progeny in lung. Wait a moment. led to the accumulation of radon progeny in lung tissue and result in the several-fold increase in absorbed dose compared to healthy lungs. Radon progeny can attach to tobacco smoke aerosols, increasing potential doses to target organs. Radon and lung cancer risk in never smokers. Lung cancer in never smokers represents around 15 to 25% of all lung cancer cases worldwide. Several epidemiological studies have observed an increased risk of developing lung cancer in never smokers exposed to high radon levels at their dwellings. Here's the category of radon concentration: less than 50 becquerel per cubic meter, 50 and 80, more than 140. Non-smokers in the cohort exhibited an excess risk of lung cancer attributable to radon exposure, with an estimated excess relative risk of 10% per 100 becquerel per cubic meter of average radon concentration. Residential radon is a clear risk factor for lung cancer in never smokers, with a significant risk observed in those individuals exposed to radon levels above 200 becquerel per cubic meter. Yeah. This is more than radon concentration to above 200 becquerel per cubic meter, compared to less than 100, almost 1.91 or 1.7. Only causal relationship with radon has been established for lung cancer. The lungs and respiratory tract receive the highest doses of ionizing radiation from inhaled radon and its decay products. Stomach and skin are also exposed, although to a lesser degree. The stomach through ingestion, skin via external radiation. Many studies have analyzed the relationship between radon exposure and cancers other than lung cancer. However, the findings regarding radon and other cancer types remain contradictory. Regarding skin cancer, the association between radon and skin cancers is biologically plausible, as radon decay products can settle on the skin, emitting alpha particles that irradiate the outer layers. Some data are obtained here: Switzerland, Denmark, Spain, United States, and United Kingdom. The results are contradictory and inconclusive, actually. But we could say ultraviolet UV exposure is a significant confounding factor. Regarding stomach cancer, ingestion of groundwater with a high level of radon is a main route for delivering an alpha radiation dose directly to the stomach. After ingestion, water is absorbed in the gastrointestinal tract comprising the mouth, esophagus, stomach, and intestines. Radon in ingested water remains in the stomach for several tens of minutes. Here is one of the data between radon and stomach cancer. Radon or radium and uranium. As I can say, as you see, no major effect of ingested natural radon, radium, uranium on risk of stomach cancer. Regarding leukemia, when radon and its decay products are transported to the bone marrow via the bloodstream, they can deliver high doses of alpha particles directly to the bone marrow tissues. Notably, radon itself provides a higher dose to the bone marrow compared to its decay products. Prolonged exposure to these alpha radiation doses can damage the bone marrow, leading to the development of immature or abnormal blood cells. White blood cells are particularly susceptible to exposure. These affected blood cells may undergo malignant changes, potentially leading to cancers such as leukemia, a cancer of the blood. There are several studies on leukemia between radon and this disease. Sweden, US, United States, Germany, UK, Denmark, Sweden, Norway. See, there are several literatures on this study. Some studies have suggested that radon may cause leukemia. Many other studies did not show statistical significance. It is, at this moment, it is not clear on this relationship. Here's a summary on this lecture. Those comes from the radon progeny. Epidemiological studies confirm that radon in homes increases the risk of lung cancer in the general population. The proportion of all lung cancers linked to radon is estimated to lie between 3% and 14%, depending on the average radon concentrations in the country and on the method of calculation. Smokers are at much higher risk when exposed to radon. Other health effects of radon have not consistently been demonstrated. This is all of this lecture.
Thank you very much, sir. So, dear participants, if you have any question, you may ask. Dear participants, if you have any question, please unmute yourself and you may ask the question. So, Tokonami sir, I think there are no questions from the participants. So, thank you very much for your such a detailed lecture on dosimetry of radon. So now we are having a break of around 1.5 hours, and we will be joining again at 1:30 Indian Standard Time, and I think 5 p.m. of Japan Standard Time might be.
Yep.
So thank you very much, participants, for your active listening. So we will be back at the same Zoom, same Google Meet link at 1:30 p.m. of India Standard Time. Thank you very much.
Thank you.
Hello, good morning. Is Dr. Tokunami is there? Professor Tokunami?
Oh, yes.
Yes, good morning, sir.
Dr. Kumar.
Yes, sir. Good morning. Sir, I was listening to your talk on National Survey of the Radon Isotope Progeny regarding lung cancer. There was a slide in which it represents, in the summary slide, it says that smokers are at more risks for lung cancer.
Yeah.
And in the slide number 214, there is a non-smokers in the cohort exhibit excess risk of lung cancer attributed to the radon exposure. Can you please clarify this bit? Slide number 214 and the last slide, that summary slide, in which conclusion is that smokers are more prone to the lung cancer. Whereas in 2114, there are non-smokers are also more prone to the this disease, that is lung cancer.
Wait a moment. Okay. 50. Wait a moment. I'll show you. In my slide 214,
Yes, sir.
lung cancer in never smokers represent around 15 to 25% of all lung cancer cases worldwide.
Yes, at the bottom there is non-smokers in the cohort exhibit an excess risk of lung.
And
in our summary, that is, there is smokers are more prone to risk.
Smokers are more prone risk.
Yeah.
So with the estimated excess relative risk of 10%, 100 becquerel per cubic meter of average radon concentration. Right? So, but let me see.
During the talk, there was one also that those who are smoking, that the person who are smokers, that may also get more exposure to this radon, resulting in some kind of cancers also.
Sorry, I don't understand your question clearly. Wait a moment.
So might be ma'am is asking that there is conflict between two of your statements in your presentation. So in one of your slides it says that smokers are having a significant risk of cancer risk development, and in your summary slide it says that they are not having any kind of risk due to radon. Am I right, ma'am?
No, that is not the case. That is, those are one case is smokers and one is the non-smokers. And
Yeah.
summary says that smokers are more prone to this. And to slide number 214 and slide number last slide, that is a summary, that is slide number 221. At slide 221, it says smokers are at much higher risk when exposed to the radon.
Mhm.
And slide number 214 says that non-smokers are also at excess risk. So, which we in case we have to compare that, which one category is more prone to cancers or any kind of other risk associated with the radon, then which one is to put first, either smokers or non-smokers?
Mm, 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 mm. Wait a moment.
Is there any correlation, or Tokunami sir, you can also explain me that is there any correlation that if one person is smoking and that is more or less, you can say less or more prone to the radon exposure and further developing any that sort of diseases associated with radon?
Mm. Let me see. Smokers. ERR 10%. Wait. Dr. Kamal, can you send me the question by
In writing box or
message? Yeah,
dialog box? Yeah,
yeah.
sure. Well, I will, sir.
I have time to consider your
Sure,
question.
sir. Sure. You can
Yeah,
let me clear tomorrow as well in your next
yeah, yeah,
session
yeah,
because you
yeah.
might be busy with other activities as I understand. I will put in the question box, in the message box, and you please take it.
Yes. Oh,
Okay.
please.
Thank you.
Yes, sir, yes, sir. But how the non-smokers and the smokers are get affected by these two? Which one will be more affected?
Yes, please. Is there anybody on behalf of Professor Rohit?
Yes, ma'am.
Yes, I have put my question in the dialog box, that is in the message box. You please transfer it to sir via email or whatever the source you people have.
Okay,
Okay?
ma'am. Sure, ma'am. Sure, ma'am.
Okay. Well,
Okay.
thank you.
Okay,
Thank you.
welcome.
Uh,
So welcome everyone after a short break, and now we are resuming the second session of this GIAN course. Professor Shiji Tokonami sir will be delivering his talk again on radon dosimetry and health risks. So I invite Professor Tokonami sir for delivering his talk.
Okay. Hello, everyone. I will resume my talk.
Uh,
Can you see my slide?
yes, sir, it's visible.
Okay. So after my talk in the previous lecture, I took a question, actually comment. So I have to modify my slide. So she pointed out the contradiction on the risk between smokers and non-smokers. But actually, as you can see, here are two total studies. The current study, just smokers study. Here is a never smokers. And look at these values. Excess relative risk per 100 becquerel per cubic meter here. So the excess relative risk for smokers is 0.28. On the other hand, the ERR for non-smokers is 0.04 respectively, with the same exposure to radon of 100 becquerel per meter. So I would like to revise my slide. Okay. So I move on to the next talk. National surveys of radon isotopes. Here's a WHO International Radon WHO handbook. This WHO initiated International Radon Project from 2005 to 2009. In this handbook, a national radon survey should be conducted using recognized radon measurement devices and techniques to determine the radon concentration distribution, which is representative of the radon exposure for the population of the country. In this handbook, difference level of 100 becquerel per cubic meter can be defended from a public health perspective. IAEA issues several documents related to radon. IAEA safety standards for radon. First, safety fundamentals. Fundamentals safety principles issued in 2006. General safety requirements, radiation protection, and safety of radiation sources. International Basic Safety Standards, 2014. Also, IAEA issued a specific safety guide on protection of the public against exposure indoors due to radon and other natural sources of radiation in 2015. GSR Part 3 does not specifically advise that a national radon survey needs to be undertaken, but rather that representative radon surveys are necessary. Representative radon surveys can be national or regional. Where activity concentrations of radon that are of concern for public health are identified, the government shall ensure that an action plan is established comprising coordinated actions to reduce activity concentrations of radon in existing buildings and in future buildings. There are two objectives in the design of a national radon survey. To estimate the average exposure of the population to indoor radon and the distribution of the exposures occurring. This can be done through a population weighted survey by measuring indoor radon levels in randomly selected homes to identify those areas within the country where high indoor radon concentrations are more likely to be found. This can be achieved with a geographically based survey. Both survey types require a different design and sampling strategy, but it is possible to meet the requirement of both in a single survey. Radon surveyed in Asia Pacific region. Radon research in Asia has intensified recently due to the growing awareness of the harm that radon poses. Based on 2019 WHO data, only Australia, China, Iran, Turkey, and Syria conducted national radon surveys. There have been large-scale radon surveys in several countries. Apparently, no meta-survey available. In Australia, a nationwide survey was conducted using solid-state nuclear track detectors. Detectors were placed in approximately 3,400 randomly distributed homes, representing about 1 in 1,400 occupied buildings for 12 months. As a result, average radon concentration in Australian homes is 12 becquerel per cubic meter. In China, the current indoor radon limit standards in China is a standard of indoor air quality, less than 300 becquerel per cubic meter. "147 cities are covered with a sample size of 72,295 houses. The residential radon concentration for Chinese cities increased over 70% in past 40 years. Here is a table, period 1980 to 1989. Sample size 21,000. The radon concentration, sample average radon concentration is 28.5. Population average 28.4. The ratio of long-term monitoring, the 4%. That means they conducted this measurement with a short-term sampling. 1990 to 1999, sample size 22,000. Sample average radon concentration 31.8. Population average 33.4. The ratio of long-term monitoring, more than 3 months, 58%. 2000 to 2009, 21,000. Sample average of radon concentration is 45 becquerel per cubic meter. Population average 47.3 becquerel per cubic meter. The ratio of long-term monitoring 61%. 2010 to 2019, the sample size 8,107. Sample average radon concentration is 54.1 becquerel per cubic meter. Population average 52.3 becquerel per cubic meter. The ratio of long-term monitoring 53%. Anyway, the radon concentration, indoor radon concentration in China increasing. China is increasing year by year. In Japan, the second nationwide indoor radon survey was carried out at 900 houses in 47 prefectures. Previously, 1980 to 1990, the first nationwide radon surveys were conducted at 5,700 dwellings. The arithmetic mean of residential radon level was 20.8 plus minus 18.8 becquerel per cubic meter. After this second survey, radon concentration is lower than the first one. 2007 to 2010, the third nationwide radon survey was conducted at 3,500 houses in 47 prefectures. The average radon concentration with seasonal correction was 14.3 plus minus 14.7 becquerel per cubic meter. Nationwide outdoor radon concentrations were measured between 1997 and 1999. The average outdoor radon concentration was 6.1 becquerel per cubic meter. This value represented 40% of the indoor radon concentration in Japan. The effective dose to the general public from radon and its progeny was estimated to be 0.45 millisievert per year. Here's a map of Japan. My city is located here, Hirosaki. There's Tokyo. So we developed a new device of radon tone discriminating monitor, which is similar to Indian radon tone monitors. Japan has been one of the leading countries in the development of radon tone detection instruments. The radiate detector has gained popularity as a discriminative radon and tone detection tool. It has been widely used in both small and large national surveys across various countries. This figure shows the aerial view, the overview of radiate. There are two chambers. Radiate consists of two chambers. This chamber is just for radon. The other one, which has large air exchange rate, by making 6 holes covered with electroconductive sponge. That means Tron entry was promoted. At the bottom, we place the CR39 as a solid state nuclear track detector. In Kazakhstan is a world leader in uranium mining. Radon concentrations were elevated due to tectonic force and geology. A total of 23 measurements were conducted in areas covered by waste rock piles, as well as in selected private dwellings and gardens. Radon concentrations ranged from 130 to 1,200 becquerel per cubic meter indoors and from 20 to 90 becquerel per cubic meter outdoors. Indoor radon concentrations were also measured in selected houses and public places near Ust-Kamelgorsk in areas rich in uranium and thorium. The indoor radon levels in these areas ranged from 22 to 2,100 becquerel per cubic meter. Here is a new project. Actually, a new project started on radon survey in Kazakhstan. This is an international joint research team of our university, Hirosaki University, Hiroshima University, Ibaraki Prefecture University of Health Sciences, Astana Medical University, and Eurasian National University. Let me introduce Asian and Oceanic Radon Association, namely EORA. It focused on radon research, education, and public awareness within the Asian and Oceanic regions. Key objectives of EORA include promoting research, encouraging studies on radon distribution, health effects, and mitigation techniques, and collaboration, facilitating cooperation among researchers and institutions within the region. I'm a founding president of this association, EORA. So if you are interested in joining our activity, please let me know. Actually, some researchers from BARC were involved in this activity. There might be a relationship between radon in soil and earthquake. So there are high seismicity regions in countries such as Japan, Philippines, Indonesia, China, and Taiwan. Still requires extensive research, especially in Asia Pacific region. This is the frequency of earthquake. Radon service in Europe. The EU legal framework on radon protection is outlined in Directive 2013-59 Euratom. In Europe, difference level is given as less than 300 becquerel per cubic meters at workplaces and dwellings. The member states are required to develop a national radon action plans addressing long-term risks from radon exposures in dwellings, buildings with public across and workplaces. Ensure measures are in place to prevent radon entry into new building. Identify radon priority areas, defined as regions where radon concentrations are expected to exceed the natural reference level in a significant number of buildings. Let me introduce a European Atlas of Natural Radiation. The project initiated and managed by the European Commission's Joint Research Center. Comprehensive maps and data sets of natural radiation levels in Europe are included. And high radon areas are identified in this map. Also, this atlas gives reference materials for radiation protection, environmental monitoring, and public health initiatives. The following maps are included, such as indoor radon, uranium, thorium, potassium in soil and rock, cosmic radiation, and ambient dose rate. So this figure shows the European indoor radon map expressed in the arithmetic mean. Here's a map on radon flux. This is the radon acceleration rate, expressed in millibecquerel per cubic meter per second. European countries initiated radon project. I am also involved in this project as an advisory board member. Radon aims to reduce scientific, technical, and societal uncertainties by initiating and performing research and technical development, integrating education and training in all research and development activities, disseminating the project achievements through targeted actions to the public, stakeholders, and regulators. Consortium, 56 partners, 20 member states plus Norway and Switzerland. Here's the starting date, September 1st, 2020, and this project will be end on August 31st this year. Rather known, the policy is towards effective radiation protection based on improved scientific evidence and social considerations. Focus on radon and norm. In Finland, Radiation and Nuclear Safety Authority, namely STUK, has conducted radon measurement in 87,000 Finnish houses and 5,000 apartments in blocks of flats. According to the measurement data, the average radon concentration in Finnish homes is 142 becquerel per cubic meter. Additionally, 70.4% of homes have radon levels above 200 becquerel per cubic meter, and 5.3% have levels exceeding 400 becquerel per cubic meter. This figure shows the map of indoor radon concentration. Less than 100, and yellow color represents 203, from 200 to 300 becquerel per cubic meter of radon. In Italy, over 50,000 measurements have been conducted in dwellings, schools, and workplaces as a part of radon concentration surveys at national, regional, or sub-regional levels. These surveys aim to characterize radon distribution in indoor air. Additionally, they sought to identify radon-prone areas as mandated by legislation. So here's the result of radon. The number of the houses and workplaces and schools. Radiolab project is a knowledge of radon gas in Italy. This project, Radiolab, is an Italian project aimed at school-age individuals. It is a nationwide initiative led by the National Institute of Nuclear Physics. The project focuses on promoting scientific awareness about environmental radioactivity, with particular emphasis on the importance of understanding radon gas exposure. Norway is considered to be one of the most radon-affected areas in Europe. The Norwegian government adopted its national radon strategy in 2009. There are two strategic goals: reducing radon levels in all buildings, reducing radon exposure in Norway as low as reasonably achievable. 200 becquerel per cubic meter as a maximum level, 100 becquerel per cubic meter as action level. Radon in Norway as 34,563 radon measurements from ground floor living rooms and ground floor bedrooms. The mean radon concentration in Norwegian dwellings has been estimated to be 89 becquerel per cubic meter. The whole Norway is affected by radon. Some areas are more prone than others. This is a map of Norway. Radon affected areas as shown at the red color. In Spain, random selection of location within the cell was chosen. Detectors were placed in ground level buildings in the main room, height 1 to 2 meters, on wardrobe separated from the walls, away from airflow and heat source. The arithmetic mean of radon concentrations was estimated to be 95 becquerel per cubic meter. Among the Spanish data, 12% of cells were in the range of 100 to 300 becquerel per cubic meter, and 1% has geometric means higher than 300 becquerel per cubic meter. This is a map of Spain. In Switzerland, the entire country is classified as a radon-prone area. Responsibility for remediation lies with the building owner except for schools and kindergarten, which must be remediated. There is no general obligation to measure radon levels, including new constructions, except in specific cases. Schools and kindergartens are required to conduct radon measurements. Radon-exposed workplaces are also subject to measurement requirements. Action level in USA is 148 becquerel per cubic meter. The Environmental Protection Agency's radon map classifies counties into 3 risk zones. Zone 1, high radon risk. Yeah, red area. Zone 2, medium radon risk. Orange color. Zone 3, low radon risk. Here. Yellow color. The Environmental Protection Agency recommends testing all homes regardless of their zone designation. The Environmental Protection Agency recommends radon testing in all homes before purchase or sale and offers resources like a student's guide to radon. NRAP 2021 to 2025 is the third installment of a strategy anchored by the US EPA to ramp up action on radon. NRAP is a National Radon Action Plan. The NRAP has established a national goal to identify, address, and prevent elevated indoor radon levels in 8 million buildings by 2025. About an average of 3,500 lung cancer deaths annually. Save approximately 250,000 lives in those buildings over the next 74 years. The USA is very aggressive against the radon exposure. In Canada, the Canadian guideline for radon is 200 becquerel per cubic meter. There is a limited radon data in northern part of Canada. Long-term radon measurements conducted in a total of 21,818 homes across communities and nationwide in Canada revealed a population-weighted arithmetic mean radon concentration of 82 becquerel per cubic meter. Here's the radon concentration in regions: British Columbia, Alberta, Saskatchewan, Ontario, Quebec. So, yeah, this is a total number of houses, 21,818. The geometric mean is 55 becquerel per cubic meter with a geometric standard deviation of 2.45. radon service in Cameroon, the focus on indoor radon monitoring began in 2012, utilizing electrolyte ionization chambers with radiate detectors being introduced in 2014. Actually, we cooperated with Cameroonian scientists. To our knowledge, radon levels have been measured in 3,000 houses. The corresponding arithmetic mean of radon concentration is 103 becquerel per cubic meter, with 49%, 9%, and 2% of surveyed houses exceeding 100, 200, and 300 becquerel per cubic meter, respectively. A National Radon Action Plan was implemented in 2020 under the IAEA TC project. This is a map of Cameroon. Dr. Mera.
Thank you very much, sir.
Maybe I need more time, but I'll move to total exposure. So after break, can I resume again?
So you may continue now if you wish.
Continue. Yes. Not so long, but 20 minutes or 30 minutes. I'm not sure. I will talk about the total exposure.
Definitely, yes, so you can continue, sir.
Yeah. After break?
After break, sir, there is session of Professor Rohit Mehra, sir. So tomorrow only you are having all of your lectures, 4 lectures are only of yours, sir. So I think either you can continue tomorrow or 10 to 15 minutes if you want to continue, you can continue right now.
Okay, may I start tomorrow? Okay.
Yes, it's okay. You can continue with your thorough lectures tomorrow because all of the 4 lectures in tomorrow's session are yours.
Yeah. Thank you.
Yes, sir. Among participants, if you have any questions, then you may ask by unmuting yourself. So dear participants, if you have any questions, you may ask.
Hi, sir. Actually, good afternoon, sir. This is not related to the topic covered in today or the day before. I was just wondering if there are any biosensors that can detect radon, and if there are, is there any advantage of it or disadvantage of having a biosensor for radon detection?
Actually, I have no idea about biosensors for radon detection.
Oh, okay, sir. Thank you.
Dear participants, if you have any more questions, please ask. So in case participants do not have any questions, thank you very much, Professor Tokonami, sir.
Thank you.
And thank you very much, dear participants, for active listening. We are having a break of 10 minutes now. So we will resume this second session of the day at 2:25 p.m. after 10 minutes, when Professor Rohit Mehra sir will be giving talks on natural radioactivity.
So, okay, we will meet at around 2:25. Okay.
Yes, sir.
Okay. Thank you, Dr. Tokunami. Thanks for the day.
Thank you.
Good afternoon, everyone. Good afternoon, everyone. I welcome you all to last lecture of this session, which will be delivered by Professor Rohit Marasar on natural radioactivity for health risk assessment. I invite Professor Rohit Marasar to deliver his talk.
Thank you, Abhishek. Slides are visible.
Yes, sir, they are visible, sir.
They are moving also.
Yes, sir.
Yeah. So, good afternoon, all of you, and once again, I welcome all of you for this last session of the third day of a GIAN program. And I hope that you might be learning a lot from the experiences or the talk shared by Dr. Tokonami, because he is having a lot of expertise in the field of assessment of natural radioactivity. And just to fill up the gap, it is my duty as a coordinator to give one or two lectures also. And tomorrow, I just want to inform all of you that tomorrow's total session will be taken by the Dr. Tokunami, and after that, uh, the last day we will be starting with the first half, that is from 10 to 1 p.m., where we have planned that you will be given a demonstration also, and you will be given hand-to-hand experience of measurement of just a minute. Yeah, measurement of uranium concentration in water samples. So we have arranged one practical demo for you people. And apart from this, let me briefly tell you that you will be given one test also, because that is a mandatory requirement as far as the GIAN is concerned. And I request all the participants to please join the Google Classroom also, because your feedback you have to share through that classroom also. And even you could submit your suggestions on the Google Classroom by writing your suggestions on a piece of paper if you are interested. But still, there are some columns in the feedback form. But if you want that you could further submit some suggestions, you are welcome, so that the next time if we could plan this type of activity, what sort of improvements you suggest that these should be included or these should be excluded. And let me make it very clear that sometimes it seems that a few things are repetitive in nature. The reason for this is like, though we are having a planned course in such a fashion that we can give you a crux of different uh, ideas, like measurement of natural radioactivity in air as well as in water as well as in soil. But we have focused, or we have done a lot of emphasis on the particular topic, especially the air and the soil component. And water, we will be giving you a live demo also. The reason for it is like, once as a researcher for this assessment of natural radioactivity, one should be very particular in having an idea that how to prepare those samples, how to calibrate those samples. Even yesterday, when I was discussing, you should know what type of energy parameters you are interested in. So, in today's talk, we will discuss those things in detail. It will be the extension of my yesterday's lecture. So, just this slide give you an idea about the radiation and the life. You can see that radiation is not a new thing. It was present since the Mother Earth, the birth of Mother Earth. So, starting from this picture indicates, starting from like 50,000 BC, I have mentioned at 2000 AD, you could see a drastic improvement in the mankind, but radiation is same. So we are under the continuous influence of radiations. Now, what are the basic effects of radiations on you people? So, generally, once we measure the effects, because like I was telling you, that this talk is basically giving you an idea about some of the terms which we are using in radiation measurements. Like yesterday, we discussed why we measure in becquerel, why we measure in gray, why we measure in sieverts, why there are different units for the assessment or measurements, though they are interconverted also. So similarly, you should understand what are the effects and what are the types of effects which we could see with our naked eyes, or sometimes we could see after prolonged exposure. So to tell you a story about it, like I visited one of the scanning center of my district, and for some scanning purpose, CT scan purpose, and I asked the person who was operating the CT scan machine that where is your pocket dosimeter? So he asked me, sir, how do you know that I have to wear a pocket dosimeter? So I said that I am basically working in this area, so that is why I know that the pocket dosimeter is very important while you perform these type of X-rays or CT scans on the patients. So he said that recently we had a call from the AERB people also. Like there was a problem with our dose calculations through that dosimeter. So I said, why? He said, actually, I have put my pocket dosimeter under the uh, uh, a tray of the patient tray where the patient is lying in the CT scan, and then continuously for whole of the day, for so many days in a month, that dosimeter goes inside the CT scan machine, again comes out, again goes inside, again comes out. So it was having a very high doses recorded. So then I said, then what is the use of wearing those doses if you don't wear a pocket dosimeter in your pocket? Because it is for you. So it is very important to make the people understand that the dosimeters which have been developed or which has been given to the radiation workers, they are very important and they should be kept along with them. So it's not possible that you keep your dosimeter in the radiation area and then you go home after performing your duties in the radiation fields. So dosimeter will be giving a different reading, and you have been exposed for a particular time, but the dosimeter has been exposed for a particular time. So it is very important to understand the basics of that these dosimeters are very important, especially while you perform any radiation related experiments, or either you work in radiation areas or you work as a radiation physicist in some of the hospitals after pursuing MSc or a PG diploma course of radiation effects. Because if you are not aware about the effects, so you can't tell the people that what are the effects of those radiations. So we have categorized the health effects basically into two categories. One are the deterministic effects, that is the severity of it arises with the dose, and for it the threshold is believed to exist. So means you could determine it directly. So like if you go for a say one chart which I have shown you yesterday, that if your dose is more than 700 millisieverts, so you bear hair losses within a span of weeks, 1 or 2 weeks. And this is actually happening once a cancer patient undergoes a chemotherapy treatment. The dose rate is very high. It is around 700 or 750 millisieverts. So that dose rate, once a person is exposed within a 2 or 3 weeks, you could see that he or she has lost her hair. So these are the deterministic effect which you could directly determine. So that is the skin injury or the hair losses are called the deterministic effects. Then there are stochastic effects. So that stochastic effects are not directly, you could say that immediately we could see it, but they are dependent. Basically, they occur randomly, and the probability of effect occurring is assumed to be linear function of the dose with the threshold. So if you see the graph also, the probability of having the effect means if you are having a dose, then directly the effect will be there. Sometimes deterministic effects depends upon the type of the body structure, the type of exposure which you are having. Now, if you see the Bragg curves, this is the Bragg curves which is giving you an idea that how alpha, beta, and gamma basically they are categorized, or how their energy reduces. That is, on the y-axis you could see that d by dx means if you increase the distance of penetration, how this energy reduces. So you could see from the figure on the right hand side that the specific energy loss along alpha track is around 100% when the distance, of course, we have not mentioned the distance here. So it is around 4 centimeter. So once you have a 4 or 5 centimeters of distance of penetration, the effect is very less. So that means the air or the particles surrounding your detector or surrounding you are the more important parameters which gives you the maximum doses. So if you have a little bit more distance, so your exposure is very less. So we will discuss that thing in our next slides also, where we will be discussing how to keep the radiations at a minimum level. So you could see from the figure on the left hand side as well as on the right hand side that for even X-rays, for even protons, so the doses get decreased when the distance of penetration is increased. Now, the radio sensitivity of different tissues and organs are also playing a very important role in having a deterministic effects on your body. Like the radiation sensitivity which I have mentioned in the table, you could see that highest is there in the gonads, like your testes, your ovaries, and then even in your bone marrow, and the lowest is there in the fats or nerve cells. So if you see from the figure, the direct exposure is different for different organs. The same dose exposed to a given body has a different impact on the different organs. So there are some medium effects on the kidney, liver, lung, and then there are some medium to low effects on the pancreas, muscles, and then the lowest effects are on there in the nerve cells or the fats of the bodies. But your gonadal tissues are very sensitive. Your even eyes, intestines, they are very sensitive for the radiations. So that is why once the radiation occur, so these organs are affected at a higher speed as compared to other organs. So you have to be very careful about selecting the radiation sensitivity. So different organs have a different type of radiation sensitivity. Then radiation carcinogenics. If you see, means what is the cause for different types of cancers which basically occur among the different body parameters. So this left hand side table give you an idea that skin cancer, the cause is X-ray bulb factory workers are exposed to large amount of radiations in the process of their work. So even X-rays could give you the radiation effects in terms of skin cancers. So if you have undergone large number of x-rays, yesterday I've given you some doses also, like if you go for an x-ray, this much of exposure is given to you. So that is why it is very important, which I was discussing yesterday, that our radiation workers or our radiation physicists who are working in the testing laboratories, especially the laboratories where CT scans are performed, MRIs are performed, X-rays are performed, they should be very aware about these things. I had a meeting with one of the radiologist. He said ki we have purchased a 1.5 Tesla MRI machine. So I asked him ki, are you aware about that how this 1.5 Tesla affects our body? He said, I'm a doctor, I need not to go into that detail, but I know it is safe for the patients. Then I said, I will send you some of the literature, and you go through that literature and you will imagine that once a person is exposed to high magnetic field, though MRIs are very safe as compared to CTs or X-rays, but high exposure of MRIs also gives you a very high concentration of radiation damages. He said, how? So then I sent him some of the literature where it was mentioned that if a human body undergoes more than 3 Tesla or 4 Tesla, so then there are very less chances that his water particles or water molecules within the body will regain their shape. So sometimes the damage could be permanent if the magnetic field is more than 6 Tesla. So though with the increase of the magnetic field, the quality of the MRI increases, but still as a radiation physicist, you have to discuss with the radiologist that if we go beyond this much of field, it could affect my body. So for that particular purposes, you should have a basic idea. Sometimes it is being asked by some of the patients or even some of researcher, sir, sometimes we go for CT and sometimes we go for MRI. What is the difference behind CT or MRI? So I'm not going into the so much medical details, but I am just giving you a basic idea that wherever it is a hard tissues or hard bones are there, CT will give you the best results. But wherever there is a fluid type of a material, the MRI will give you the best results. Because magnetic resonance imaging is based upon the dilation of your water molecules within the body. So that is why wherever there is a fluid type of a material is present inside the body, then MRIs are preferred. Suppose if a person has undergone an accident, so suppose he has a brain injury, the best way is to have an idea that whether his skull is safe or not. Skull is very hard. So firstly, the doctor will prefer to go for a CT. So if within the CT he finds some problem, then he will prefer to check the body fluids or the fluid present inside the brain. So there he will prefer the MRIs. So depending upon the type of measurements which you are performing either on the solid surfaces or on the fluids present in the body, so you decide with the CT or the MRIs. So then different cancers I have mentioned that lung cancer, miners in uranium mines inhaled radon by breathing, and then they could be affected with the lung cancers. The reason for it is lung cancer, why it is called by the radon exposure. It is the second largest cause of lung cancer after cigarette smoking. So the second largest cause after cigarette smoking is the radon for the lung cancer activities. Then there are some liver cancers, also there are some exposures. So depending upon different types of risk parameters, so radiation exposures, so you could have different types of effects. Now, objective of radiation protection means how to keep the radiation exposure minimum. So to keep the radiation exposure minimum, of course, one thing is like yesterday we were discussing, within the dwellings, within the houses, within the offices, you could have a better choice of ventilation conditions. You could have a better choice of building materials which give you lesser exposures. But apart from this, there are some parameters which we generally call as ALARA, that is as low as reasonably achievable. So, to prevent clinically significant radiation induced deterministic effects by adhering to dose limits that are below the apparent or the practical thresholds, we have to follow the ALARA. Now, the limit to limit the risk of stochastic effect like cancers or hereditary effects to a reasonable level in relations to the societal needs, values, and benefits which are being gained. Again, we have to follow the ALARA. Now, ALARA has a one objective to keep the radiation as low as reasonably achievable. So, this is the full form of ALARA also, as low as reasonably achievable. Now, what are the three fundamental principles to keep the radiations as low as reasonably achievable? Is the first is you minimize the time of radiation fields or radiation exposure, which we were discussing, that if you are having a disintegration in a particular room, I will not be affected unless and until I enter in that room. So if my exposure is minimum, if I have no exposure of a radiation field or radiation area, so my exposure will be less. So second is you maximize the distance from the radioactive source. So sometimes if mine workers are there, if some radiation workers are there, or if some radiologists are there, or radiation physicists are there who are working with radioactive sources, they could increase the distance. So with the increase of distance, the radiation exposure again becomes lesser. So third is you should use a radiation shielding. So radiation shielding means like you might have performed experiments in your graduation classes also, while you perform some experiments related to the GM counters, where you could keep your sources, alpha or beta sources, within the lead shields. So you might have seen some cylinders of lead cylinders where you could keep your sources, and the detector is present within the lead sheet, GM tube is present within the lead sheet, and it is not affected from the background. So you could use some radiation shielding materials. Now, principle of radiation protections, which we were discussing in terms of ALARA. So time, you reduce it, you will get the lesser exposure. And distance follows the inverse square law. So suppose if your distance is 2 meters from the radiation source and your exposure is say X, if you increase it from 2 to 4, your exposure will be, because your distance has increased 2 to 4, that is double. So your exposure will be square, that is 4 times it will be reduced. And if you increase the distance 3 times, from 2 you make it as a 6 meter or 6 centimeter, your exposure will be 3 square, means it will be reduced to 9 times. So distance also plays a very important role, and it follows the inverse square law, means if your distance becomes double, your exposure becomes 1/4. If your distance becomes 3 times, your exposure becomes 1/9. If your distance from the source becomes 4 times, your exposure will be 1/16 times. Reduced exposures will be there. Now, for the shielding purposes, lead is one of the examples, but even yes, yesterday, which we were discussing, Fly ash bricks can also act as a radiation shielding material sometimes, because they also absorb so many radiations. But still, the preferable materials are the lead aprons, which we generally wear while performing even some X-rays or other medical diagnostics. Now, the purpose of estimation of radionuclides in soil. So, I will be telling you in details that what type of energies we are focusing, and how we could measure the primordial radionuclides in soil. And basically, we are focusing in three categories: radium, thorium, and potassium in soil samples. And then, like yesterday we discussed, we convert those radium, thorium, and potassium in terms of radium only, that is the radium equivalent, and finally calculate the things. Here we will be discussing the details of that. So if you see the first figure, the soils are collected from the bottom. Actually, what happens if you collect the loose soil or the upper soil? Sometimes the local effects plays a very important role. Suppose you have placed the pesticides, and during that season, if you extract the soil from the upper surface, that pesticide may give you high level of exposure, which actually the soil is not having similar exposure. Like if you sprinkles potash during the agriculture seasons in the agriculture fields, so potassium levels will give you a very high value. So it is preferably recommended that you collect the natural soil at a depth of around say 0.7 to 1 meter from the ground. Then you crush that soil and make it a fine powder, and sieve it accordingly, and keep the temperature less than 40 degrees Celsius. You dry it within the shady area, and after that you make it as a oven dried for 3 hours or 2 hours, depending upon the type of moisture your soil is having. Then you sieve it and finally pack it with particular weight. Like this sample holder is having a 150 gram of weight. So weight also plays a important role, because your detector and the geometry of the detector also plays a very important role. Sometimes we collect 250 grams, sometimes we collect in a marinal beaker, we collect nearly 1 kg of soil. So it depends upon what type of container you are using. So like for this particular container, it is around 150 grams. Then you store those samples to attain the radioactive equilibrium, so that the parent and the daughter equilibrium is obtained, and finally whatever you get, so that is the nutshell effect of the radiations which are causing directly from that particular soil. Now, this is the parameter which we are working in, and this detector has a resolution of around 7% for cesium at 262 keV with the activity of 9 kilobecquerel. And you see the efficiency is very less, so but 20%. But generally for radium, thorium, potassiums, its efficiency is high as compared to the cesium. So yesterday we were discussing that you should know for what type of energy you are measuring. So like we were discussing HPG as well as scintillation counter on one day, that for HPG the resolution is very high, and for a scintillation counter the efficiency is a little bit higher as compared to HPG. So why we require the high resolution means, if we want to determine some very nearby peaks, suppose I want to have an idea of an element having energy of the order of 180 keV and another element having energy of the order of say 200 keV. So then quite possible my scintillation counter cannot resolve those two energies. So, but HPG, though it is having lesser efficiency, but its resolution is very high. So depending upon the type of requirements, either resolution or your efficiency, you could compromise between two different detectors. And if you see from the previous figure, so we evaluate the radium 226, thorium 232, and potassium 40 with the different peaks. One for radium is we generally use 1764 keV of peak with our detector, and for thorium we prefer 2610 keV of peak, and for potassium we prefer 1460 or 1461 keV of energy peak respectively. Then activity concentrations are calculated, and these are the graphs. Actually, if you see the graph, so this is the calibration which we have done with our RG samples. So we know some known standards of soils where the activity concentration of uranium, thorium, and potassium. Uranium is basically the radium which we are mentioning. So radium, thorium, and potassium is recommended, and by known value of samples we calibrate our detector, and we try to calibrate the peak with the cesium also. So before starting an experiment, the calibration is very important, that your detector's peak, like I know there is say uranium source of say particular energy, say 1763 peak. So I will fix this vertical line to such a value and adjust my voltage and potentials such that this line comes in alignment with the peak. So before performing an experiment, like for thorium, it is 2610. So I will align this line to that 2610 peak. Like here it is 2610, say peak is there. So across x-axis there is an energy, and across y-axis there are the counts. So gamma counts, scintillation counts. So you have to calibrate your detector before performing an experiment, so that with the known source, if you are having a known source, then only you could calibrate, and you have to adjust this vertical line in alignment to the that peak. Now, if you see again the energy spectrum of cobalt 60 and cesium 137 isotopes, it is again corresponding to the different peaks. And like yesterday, we were discussing that as a physicist, we should know that how to estimate it. We have to calculate the area under this peak, and finally, we have to measure the FWHM value, that is full width half maximum value, so that we could calculate the probability and the activity concentration depending upon the different materials. Now, this is just a particular physics behind that, which I am telling you. Suppose at this corresponding to 252 or 256 or 261 keV of peak, there is a peak which is coming. So I have to calculate the FWHM value, full width half maximum value. So I could manually do the curve fitting techniques, or nowadays the softwares are available which do the calculation in such a fashion that they do the curve fitting techniques and finally calculate the area under this peak, and based upon the area under the peak we calculate the activity concentration. Now, the full width half maximum obtained from the experimental work of sodium iodide detectors. So you could see that full width half maximum, we suppose there is a peak corresponding to this value 261. So how to calculate the full width half maximum? Firstly, we have to take the maximum value, and then we have to take the half of it. Here the maximum is around, say, 15,000 to 16,500. It is around 16,000, I could say. So within the 16,000, I will take the half of the counts as, say, 8,000, and then I will draw this line. So this is the half H2. So at H2, I will draw again a line, and then draw some corresponding lines to different energy values. And if you see the full width half maximum, so this full width half maximum is minimum at around 636 keV and maximum is at around 685 keV. So if you see the cursor, this is the firstly full, that is around 16,000 counts. Then we have taken the half of the count, that is around 8,000 counts. Then we have drawn a line corresponding to this, and then we plotted the line corresponding to the y-axis parallel lines and touch the energy values. And the energy for the minimum is around 636, for the maximum is around 685. So this is the FWHM, that is 685 minus 336, that is 49 keV. Now we have to calculate the resolutions, energy resolutions. So energy resolution is basically the FWHM value which you calculate. Of course, it is being done by the software. You need not to worry about it, but you should know the physics behind it. So then EO, you have to divide it. That is energy central of photo peak. So energy central of photo peak is around 661. This is the maximum peak, 661. So we divide this 49 with 661. So we get an R, that is the value responding to the percentage. So that is around 7.40 percentage. Now, these are the peak energy of gamma spectrum measured from about 661 keV of photo peak of cesium, because cesium gives you an idea of 661. Cesium is generally not practically should not be available naturally, because unless and until some nuclear fallouts are there. So, but generally cesium is given as a calibration source to all the vendors to the experimentalist, so that they could perform the calibration standards. So otherwise, naturally you will not get a cesium unless and until some nuclear fallouts are there, or there is a error in your instrument. So you should not get the cesium. So, but generally it is given by the vendors along with the instrument to perform the calibration standards. And mind it, the calibration is it's not a thing which you could understand within a single lecture, because it is very difficult. So you have to adjust voltage and current so many times to get your peaks aligned with the particular energy. So, but with your experience, and if you are having a basic knowledge of physics, you could always do the calculation and do the manipulations with the experiment, and you could adjust your instrument to be calibrated across the photo peaks which are given to you. If you see from this arrow, this is 1461 or 1460 is a peak which is corresponding to the potassium. Similarly, 1764 is a peak corresponding to the bismuth. Now, is this peak corresponding to the bismuth is basically coming from the radium. So if you see from this, radium generally we calculate in terms of 1764 keV of bismuth peak, and thorium we generally calculate into 2610 keV of thallium peak. So that is why it is very important that yesterday I gave you an idea that what are the series which you should remember, because if you are miring what type of element, you should know that my radium is coming from, after my radium is coming, what type of peak is available to give me the gamma energy. There I have shown you some alpha, beta and gamma decays with the arrow indications. So if radium 226 is there, then the gamma peak will be coming from 214 instead of 226. So that is bismuth is responsible for giving you, because this is a gamma ray spectroscopy. It is not an alpha spectroscopy. So you should understand what type of spectroscopic technique you are using. And sometimes it is being asked also, like, sir, what is spectroscopy? Spectroscopy, if you talk in a layman's language, it's just a field where you do the analysis based upon some orderly arrangement. Now, what is spectrum? Spectrum is orderly arrangement of something. Like if I have an orderly arrangement of frequency, so I call it as an electromagnetic spectrum where there are a lot of frequencies are involved. So if I have orderly arrangement of masses, I call it as a mass spectrum. If I have orderly arrangement of frequency, I call it as a frequency spectrum. If I have orderly arrangement of energies, I call it as an energy spectrum. So you should understand that what type of performance you are performing, and if I am having a gamma ray spectroscopy, I am having orderly arrangements of the gamma rays coming out of some of the materials, and that spectrum may be absorption or emission. Again, it is a physics which is a long process, so which you basically understand, but you should have an idea that what is spectroscopy. It is a measurement or a technique which is basically used to have a study of something orderly arranged. If it is mass you are studying, it is a mass spectroscopy. If it is energy, it is energy spectroscopy. If it is a gamma, it is a gamma spectroscopy. So gamma values, if you are measuring, then it is a gamma ray spectroscopy. So this is how, by doing the FWHM values, we are estimating the E values, that is activity concentration. So the specific activities depends upon the net count rate under the piece, and then time T represents the measurement times in seconds. Then I gamma represents the energy intensity of gamma ray. Similarly, Xi is the efficiency of the detector, and M is the mass of the sample. So that is why I was saying efficiency will be different for different peaks. So you have to calculate FWHM value efficiency for every peak. Of course, you as an experimentalist, generally nowadays it is all computerized. We need not to do any calculations, but just for your basic knowledge, I am telling you that you could always calculate the efficiency for a particular energy, and then the branching intensity involved with that particular energy. There are tables available on the websites, there are tables available on the internet where you could find out that what are the different energy parameters. And mind it, my friends, you should understand the people who are working in the field of nuclear physics. The ICRP, that is International Commission of Radiological Protection, keeps a record of all the people who are working in the field of nuclear physics, especially. And it keeps the logging of all the publications which have been published by those people. After this lecture, I will tell you one example that how you could see the database that which people are working in the particular area. So you could have an idea that they keep all the records, all the tracks. If I have attended one conference, what type of paper I have presented. If I have attended, published one paper, in which journal I have published. I will show you after this lecture. Then again, yesterday, which we have already discussed, we calculate the radium equivalent and then the external or internal hazard index. And there is the next part is we can measure some radon mass exhalation and the radon surface exhalations from the soil samples also. Now, exhalation or emanations are basically two things. Exhalation means if the soil is having some radon concentration within the soil, I could also measure that radon and thoron within the soil. Like Tokonami sir was discussing lot of things, or even I have discussed in one lecture that how the pinhole cup dosimeters are used, or DTPS or DRPS are being used to estimate the radon concentration in air. But radon may be present in the soil also, because soil contains so many radioactive materials, and if that soil contains radioactive materials, So once the radioactive decay occurs, so those soils will also generate the radon or thoron. So we could select these two instruments which have been indigenously developed in India, a smart radon dew, which are the portable radon and thoron monitor. So it has been indigenously developed in India by the BRC with the help of some vendors, and now they are patented with the BRC. You could always go for the purchase of these instrument radon smart dew, where some of the BRC people, a BRC group, are working, and they have developed this instrument. Just a very simple instrumentation is there, that there is a photo multiplier tube. So they are, after some times, after some days, the radon or the thoron is coming, and it is giving some scintillations in the scintillating material which is present, and then those scintillations are passed to the photomultiplier tubes, and then after this, the photomultiplier tubes, the diodes arrangements are there and the counts are being increased. So you could measure the exhalation in two different modes, diffusion modes and also in the flow mode. So depending upon this, I have performed one of the case study in Shimla and Solan districts of Himachal Pradesh, and we have found that in Shimla we have selected nearly 12 samples, and in Solan we have selected nearly 13 samples. And you could see from the table that in Shimla, the radium activity gives me the maximum value of around 73 becquerel per kg. The recommended action levels are basically 30, 35 and 400. 30 for generally radium, or you could say 35 for radium, 35 to 40 for thorium and 400 for potassium. So this is the recommended values. If they are beyond these recommended values, then it is a cause of concern. Means that soil, if you are using those as a building materials to make the bricks or even used in the houses, that is a cause of concern. So it should be within the safe limits of 30, 35 and 400. That is radium up till 30 or to 35, potassium up till 35 to 40, and thorium to 35 to 40, and potassium up till 400 becquerel per kg. So in most of the samples, they are within the safe range, except from one or two samples. So where the detailed analysis was again designed with the help of some estimation in the water samples, estimation in the air also. So we have performed different experiments. Like surface exhalation or mass exhalation, if you see, personally speaking, if I say that mass exhalation is more important parameter as compared to the surface exhalation, because surface exhalation is not a parameter which is in your control, because this gives an idea that what type of container I am using. So if my container is little bit more flat, if you see this container, if my container is a little bit more flat, so its breadth will increase and height will decrease. So the A value, that is the surface value, will be different. Surface will be different. So if it is a skier type of a material, the surface will be different. So it is better to go for the mass exhalation to have a better idea, because mass, we know that we have used this much of soil and this is the mass exhalation. Surface is little bit depending upon the geometry, so which you need not to worry a lot. Now these are the spatial variations which we have plotted of activity concentration of radium, thorium and potassium in the soils, and you could see that the values, if it is more than 60, they are plotted in different color. If it is less than 45 they are plotted in different color in case of thorium, similarly in case of radium, in case of potassium on the upper side. And this is for the Shimla district. Green is for the radium, and this orange color is for the basically thorium, and this blue color is for the potassium. So we have spatially distributed whole of the districts in such a fashion that you could have an idea that how the grid mapping is being done. So we have mapped nearly, our lab has mapped nearly more than 70 districts till date. So where we have this spatial distribution map across all the 70 districts in the northern India, including Himachal, Rajasthan, Uttarakhand, Punjab, Haryana, and some parts of NCR also. So we have mapped a lot of districts, and our group has done a lot of studies in South also, where we have mapped some of the districts of Kerala, as well as Kalapakkam area, where our atomic power station is also situated. So you could have an idea that from this spatial distribution map, directly you could have an idea that this area, say, is a little bit more safer as compared to the dark regions. So of course, the cause of concern is if it is beyond some permissible limits, like 30 in case of radium and 40 to 45 in case of thorium, and more than 400 in case of potassium. So again, just a comparison with the bar graph, we have shown that study region average is around mentioned in Indian yellow color. It is a little bit more than the Indian average, but equivalent to the world average in case of radium. Similarly, for thorium, for potassium, the areas are matching, the values are matching with the world average. In case of radium and thorium, it is little bit more as compared to the Indian average. The reason is the geology of that area. They are the shivalics, middle shivalics, so which are having a little bit high concentrations, and it has been reported by so many workers. So this is the unscares values which I was discussing, around 30 to 35. They have mentioned 33. So that is why I have given you one range. Similarly, 45 in case of thorium and 400 in case of, or 412 in case of potassium. So these are the values which have been recommended as a average values. It should not be more than this. If it is more, still it doesn't mean that you are in danger, but you are little bit having more exposure. So again, we have done some spatial distributions by calculating the annual intake doses, and then our annual exposure in terms of civets, that is how it is affecting our body. So we have calculated and presented our results. And of course, there is a difference of exposure to the dose conversion factors for different categories of people. Like for adults, if you see the annual estimated dose, if you see the DCF values for adults, it is 0.7 sievert per gray. For children, it is around 0.85 sieverts per gray, and for infants, it is around 0.9 sieverts per gray. So you again have to use these particular values of dose conversion factors for the category of the people where you are calculating. Then these are the box plots for adults and average. And these are the conclusions. Basically, the adults, infants are the more significant radiation affected people, and among the even organs, I have mentioned that bone marrow, lungs, ovaries, testes, they are the important organs which are affected by the radiation exposure. Similarly, which I was discussing with you, that I will show you one activity in such a fashion that how those records are being maintained by IAEA. I think just a minute. I have left the meeting. Just a minute.
Hello. Sir, actually, you're not audible, sir. Your mic is mute.
Okay. Sorry. Just a minute. Yeah. Now I am audible.
Yes, sir.
Ah, so I was telling you that basically this is the agency who is keeping the track of all the things. That is the International Nuclear Information System is there. So which is keeping track of all the people who are working in the field of radiation area. So I was just telling you that you could have an idea of any person who is working in the field of nuclear science. This record is being maintained by IAEA, that is the International Atomic Energy Agency. And if you see from this, I have mentioned one of my name also, like Rohit Mehra, and you could see that I have published in these subjects. Atomic molecular condensed matter physics, nuclear materials, nuclear physics. So nearly this much of journal articles are there which have been taken as a record by those INIS references. Then publication years, you could have an idea that nearly, say, I click for 24. So these are the publications which are published in, say, 24. So you could always have a in-depth analysis of a particular person who are working, like my student Aarti is working. So this is their radiation protection and dosimetry is there. So from where it has been published, the journal is the Journal of Radionet Analytical and Nuclear Chemistry. So all the records are being kept by the IAEA. It means if you are working in this area, you are under the eyes of IAEA, Atomic Energy Agency. So say I mention another fellow of my colleague. So he is Harish Mohan Mittal, my colleague. So I will get his information, that how he is published, where he is published. So if I mention, say, my student, so I there you have to do some filter also, like one of my students is Pargan Bangotra, say. So it will give the results. So this is our paper which we have published. This is again a paper which we have published. This is again a paper which we have published. So you could have an idea that what type of publications we are doing, what type of publications the people are doing. So that gives you a basic idea of the repositories. So you could always search for those repositories. So with this, I finish my today's lecture, and if any queries are there, you are welcome.
Hello, good afternoon, sir.
Good afternoon.
Sir, I have one query that the Alara principle that is valid for the, I mean, like medical exposure, or it is also for the natural radioactivity?
It is also for the natural exposure, but for natural, actually, I have already told you. And for natural, you are being exposed by the surrounding airs around you and surrounding soil parameters around you. So
Right, sir.
that is also applicable, but exposure is less. So that was one of the protocol which we suggested while hanging our pinhole cup dosimeter, that you should keep it away from ceilings as well as the wall. Centimeter exposure comes to zero value. So it is applicable mostly in case where some radiation workers are working with the radiation sources, but naturally it is also applicable.
Okay, sir. Thank you. Sir, there is one other thing is LNT model.
Mm-hmm.
So LNT model also holds for those workers, or including natural radioactivity.
That is very much applicable, but actually the problem is the purpose of this principle is to keep the radiations minimum. So the best way is you increase the distance from it, you reduce the time, because shielding is not in your hand. Shielding is within the hands of the people who are doing some things with the radiation sources. So as a layman or as a public, you can't go for the shielding. What you can do is only wear some aprons or clothes while you are going there. So shielding part is basically dealt with the people who are working in the nuclear fields, but your exposure time you could reduce, your distance you could increase, so your exposure will be lesser.
Okay. Thank you, sir. Thank you.
So any other question?
Good afternoon, sir. Sir, I have a small, question. It's just on the curiosity side. If there is some nuclear war, sir, let's say in Europe or somewhere, maybe you say 4,000 kilometers away,
Yeah.
and the size of the nuclear bomb is maybe, let's say, 20 kilo TNT.
Yeah.
Like how we, is the radiation come over to this place, or if it comes, then how we should save it little bit, by doing some jugaad or something like that.
Like I was telling you, sir, during the discussion also, generally we don't get the cesium exposure in naturally. Okay. So cesium, if you are getting some cesium, so probably it is due to some nuclear fallouts. So one thing is the continuous monitoring which is being done by so many agencies, like in our institute we are also having a continuous 24/7 365 days monitor. So which is radon geostation we have placed or installed with the help of BRC people. It is simultaneously done across all the places at a distance of say 100, 200 kilometers away from each other, so that within India we could cover it. So if even some activity within the range of say 80 kilometers from my Jalandhar area, suppose some nuclear activity is going on in terms of Pakistan even, so that continuous monitoring will at least detect some cesium activities. So if little bit cesium activities are on a higher side, so that is a cause of concern. So then we do some other experimentations, which is not in our control. Actually, that is a Department of Atomic Energy's problem is there. So if there is a fallout, nuclear fallout or a nuclear exposure is there, quite possible even in Russia or Ukraine war, if they use some nuclear weapons, quite possible you could have some nuclear fallouts within the surrounding areas. But your distance, I have told you that if your distance becomes double, it becomes 1/4. If it becomes thrice, it becomes 1/9. But continuous monitorings are being done by all the countries, sir.
Thank you.
Okay, ji. Then we can close this session, and tomorrow whole of the sessions will be taken by Dr. Tokonami. And day after tomorrow, we will be giving you one lecture and then having some little small tests, you could say. And Besvijit, you want to ask something? Besvijit Behra has raised his hand. So anyways, if you have some queries, we will discuss it in the next talk also. We have a continuous process of logging and recording your comments also, and we will answer those queries. Thank you once again. Thanks a lot.
Thank you, sir.